This is a review over the lab we did with the person walking across the room with the apple. It's kind of difficult to do this one because it was such a simple lab. So there's no real drawings to do. The important thing to remember is that you had a point here and a point here representing the meter stick, and a point here, points like this representing the distance that they traveled. Okay? Now, the important thing, hopefully, you took away from the lab is that if these points are evenly spaced, then they mean they go at a constant speed. So if the points are evenly spaced, it's constant speed. So that's hopefully what you took away from it. We did a lot more with this, though. We tried to actually figure out what their speed was. We did a scale factor. So I'm going to try to mention these things just to make sure that you remember them. And if you weren't here that day, hopefully you can get the notes from somebody, but maybe hearing me say this will help you understand what we did. So the first thing we did is we had to determine how fast, or rather, how long it took them to get from their start to the place where they ended. And the way we figured that out was I had a camera, or rather a strobe light, that was flashing 5 times per second. So 5 times every second the light would flash, which means that the light was flashing every 0.2 seconds. And what that means is that the space between each of these dots was 0.2 seconds. So in order to calculate how many or how long it took, the time, I just counted up the spaces between my dots. So for this one that I've drawn here, this would have been 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6. So for the one I've drawn, 1.6 seconds will have passed. All right? So we've done this. We know that 1.6 seconds passed. We know that for every flash, every space between those dots, 0.2 seconds passed. All right? So we've got this data. All right, now let's see what happens. Most of us got a graph that looks something like this, where you had dots that were kind of going in the same direction, but they weren't quite going in the same direction. They weren't quite straight. So what we had to do was we had to make a best fit line. And what a best fit line is supposed to do is not quite that. Let me try one more time. That's a little better. A best fit line is supposed to get equal numbers of dots above and below the line. So here I have 5 dots, so clearly that's not quite right, but it's close enough. This is the general speed she was going. We could almost say this is her average speed, the speed she was averaging. And it's important to do a best fit line because it kind of evens out any discrepancies you have in your data. She might have stopped, or he might have stopped, he might have slowed down. Something might have happened, might have just moved their shoulder a little bit, and it messed up the data. But if you draw this best fit line, it smooths out the data. So we drew the best fit line. We found the slope, and we found that the slope was equal to their average velocity. But what we found is that the average velocity was in centimeters per second, because we measured in centimeters. So because we were doing this on a piece of paper, we weren't doing it in reality. So let's just say that we got our average speed to equal 10 centimeters per second. Now, she is not moving that fast in reality. She's moving much faster. We have it scaled down because it's on paper. So what we needed to do was to figure out how fast in reality 10 centimeters per second was. So we came back here and we used this meter stick. We knew this was 1 meter in reality, and we found that it was some distance on paper. To make things simple, I'm just going to say it's 10 centimeters on paper. All right? So on paper it was 10 centimeters. In reality, it was 1 meter. So the meter stick in reality was 1 meter long. On paper, It was 10 centimeters long. Okay? So what that means, if 1 meter is 10 centimeters on paper, then for every 1 centimeter on paper, it's 1/10 of a meter. Hopefully this makes sense to you. So let's look at this. If 1 meter is 10 centimeters on paper, then 1 centimeter is 1/10 of a meter. So at 2 centimeters, I'm at 2/10 of a meter. 3 centimeters, 3/10, 4, 4/10, 5, 5/10, 6, 6/10, and so on until I get to 10 centimeters. Then I'm at 10/10, which is equal to 1 meter. So this is the conversion we can use. 1 centimeter on paper is equal to 1/10 of a meter in reality. Now on paper, we got that she went 10 centimeters per second. So what I'm going to do is I'm going to try to figure out what 10 centimeters per second in paper looked compared to reality. Now, we have this conversion. We're going to use this right here. Every centimeter represented here is equal to 1/10 of a meter in reality. The seconds don't change because that flash rate didn't need to be scaled. I didn't have to scale it. It just is 0.2 seconds per flash. So what I have to do is I have to say 10 centimeters per second is, and then I multiply that by the conversion here. So if we wanted to do dimensional analysis real quick, you could see it a little better. 1 centimeter on paper is equal to 1/10 of a meter in reality. So the centimeters are canceled, and I'm left with meters per second, and 10 over 10 is 1. So her actual speed would have been 1 meter per second. All right? This is a review of that lab. Hopefully you got it from somebody, and if you did not, hopefully this helped explain what happened in that lab. All of these things are critical to know for the test coming up on Monday. All right, so hopefully this helped everybody. Sayonara.